Thank you very much, thanks Monkey and Musil for the chance to speak here, and thank everyone for coming. Today, I will talk about equals for super YAMLs in top-down, which means in string theory, which are doubly holographic, based on two papers with Christoph Wurman. So in this talk, first, I will talk about why we want to study such BCFTs in string theory, and then I will focus on supersymmetric localization, where, okay, it's a matrix model, and I will talk about the BCFT matrix model. And in the end, I will talk about some observables such as one-point functions, free energies, and Wilson loops. Okay, let's start. So there can be two independent motivations to study conformal field theories with boundaries, defects, or interfaces. Here I correctly refer to as BCFTs. Firstly, in the real world, all the systems have boundaries and defects, and it's a more realistic system to study than pure quantum field theory. And but in this talk, I will focus on the second motivation, which is double holography. This is a method to geometrize some quantum gravity effects, and applications includes black hole studies, which I will talk about. So I will introduce double holography in simple bottom-up models with some Karch-Randall branes. Let's start with the BCFT, where the boundary itself is holographic. And there are two different ways to apply holography. The first one is to apply holography only to the boundary degrees of freedom. In this case, we have an ADS brane attached with the ambient CFT with the same dimension. And one can also apply holography to the combined BCFT system. And we get a higher dimensional ADS spacetime end by end of the world brane. And in this way, we have three different prescriptions which should be equivalent. And well, the applications, as I have said, is to study some quantum gravity effects. So in principle, the quantities which lives on the Karch-Randall brane, the quantum corrections can be studied easily using double holography. So the first example is the Hawking radiation. So consider a black hole coupled to some bus which collects the Hawking radiation. And the quantum corrected entangled entropy can be studied by the RT surface in the bulk, which is very simple. And there can be other observables which on the brane to be studied. For example, in a recent paper, we studied some quantum corrected black hole microstates living on the brane. Okay, this bottom-up model is very simple and very powerful, but there are some caveats. For example, there is no microscopic definition of the brane in the sense that we know the action and we know what the matter contents. And there are some causality puzzles in this model in the sense that the null geodesics in the bulk travels faster than the one from the boundary. And the solution to them is to construct double holography in string theory. And the first step is to do ADS BCFT in string theory. So, okay, this is a review like how ADS BCFT works in string theory. We need a stack of n D3 branes, and there are two different ways to see them. One is supergravity, and one is the world volume field theory. And in the end, we have ADS BCFT. And to get ADS BCFT from string theory is very similar, but with some extra things. So in this case, the D3 branes needs to end on or intersect D5 and NS5 branes. So the first table is the brane orientation. There are three common directions which can be thought of as a three-dimensional quantum field theory in the intermediate region. And on the left and right region, there can be some semi-infinite D3 branes, which can be think of as some super YAMLs on a half space. And collectively, we get some super YAMLs, but with some defects or boundaries in the middle. And there are two different ways to see them as well. The first one is to see the world volume theory living on the D3 branes, which is n equals for super YAMLs, but with 1/2 boundary condition, and which is given by Gaiotto-Witten. There is a second way to see them is supergravity. It's given by ADS4 vector product or S2, and a sigma. So then I will talk about the BCFTs and the supergravity. For BCFTs, so this is a very simple plot for the so the left and right red lines are the ambient super YAMLs, and in the middle we have a three-dimensional quantum field theory. And the matter contents can be retrieved directly from the brane orientation by the open strings attached on the D3 branes or attached between the D3 branes and the D5 branes, which in the end can be represented by a quiver diagram given by here. And on the left and right side, the UN node with the head is the 4-dimensional super-YAML gate node, and in the middle is 3-dimensional gate node. And the K1 to KL are some hypermultiplets represented by D5 branes. And then I will talk about the gravity description. So as I said, it's an ADS4 Wapler product solution. And this solution has non-trivial type 2B fields such as Dilaton, NS, and the Ramon fields. There is also manifest S-duality symmetry, which I will introduce later. The important thing is that all the information about the gravity solution is given by two harmonic functions living on the 2-dimensional strip. So this is a strip, and on the top and the lower boundaries are the D5 and the NS5 sources. And the important thing is that on the left and the right boundary, there are two possibilities. So in this example, on the left boundary, the geometry closes smoothly and becomes an ADS4 solution, ADS4 times B6. And on the right-hand side, the metric can blow up and becomes an ADS5 cross S5. So in this case, on the right-hand side, there is a 4D super YAML, while on the left side, there is no 4D super YAML. It's 3-dimensional, and it represents the holographic duo of BCFTs. And these are the two harmonic functions. The first term encodes the asymptotic behavior on the left and the right boundary of the strip. And the second term encodes the source of the 5 branes. And what I said about S-duality is that one can trade the upper and the lower boundary and trade the H1, H2 at the same time, and the solution will remain unchanged. So this is a way to, in your S-duality, to swap D5 and S5 branes, NS5 branes. Okay, I have talked about.
Can I check something about that? Are the fibrine sources, is the back reaction taken into account, or?
Yes, this is a fully back-corrected solution.
Okay, good. So the NS5 is replaced by some flux, and the full gravity solution is found.
Yes, okay. They have non-trivial fluxes and dilaton.
Okay.
Yeah.
Good, thank you.
You're welcome. Thanks for the question. Okay, now I have finished the ADS BCFT, and I will talk about how to construct a double holography from this system. So again, let's take a step back and look at this BCFT, where these are the semi-infinite D3 branes represent the 4D super YAMLs on half space, and this is the 3-dimensional superconformal theory, which can be engineered by grooving this pure 3-dimensional theory and the 4-dimensional super YAMLs by gauging the flavor symmetry, where the flavor symmetry is to terminate the D3 branes by some D5 branes, and we have some flavor symmetry. And in the bottom are the holographic duos. So this is ADS4, ADS5, and this is ADS4 and ADS4, which is purely 3-dimensional. And the gauging can be think of as this partition function. So we start with the 3-dimensional SFT with some flavor symmetry, which has some conserved current, which is coupled to some background gauge field. And we also have some 4-dimensional super YAMLs, and we can think of the background gauge field as the boundary value of the 4-dimensional gauge field. And then we carry out the path integral, and we get the partition function for the full BCFT system. And to get to the double holography, we use holographic dictionary only to the 3D, the defect degrees of freedom. So we treat this safety by the string theory partition function or supergravity partition function on ADS4. And in the end, we obtain the partition function with a brane coupled to the ambient CFTs. And in a sense, we have Z equals Z equals Z. So we have specified the action for the end of those branes, and we have also specified the dictionary of double holography. And as applications, this prescription can resolve the causality paradox that I talk about, but I will not introduce the details here. And we can also perform the island and the page curve computations in the top-down setup and get similar results as in bottom-up models. So now I have finished the review and the motivation, like why we want to study double holography in string theory. And now I will move to the BCFT side in top-down and use the method of supersymmetric localization. So this is a brief review to people who don't know supersymmetric localization. So suppose we want to compute the expectation value of some supersymmetric variables O, which is protected by this fermionic symmetry. And we can deform the partition function by a potential, which is also in the cohomology of the supersymmetry. And one can find that the wave is unchanged. By taking t to infinity, we can find the wave is also still not unchanged. But then this partition function is dominated by the side point of the potential. And then we reduce the infinite dimensional path integral to a finite dimensional matrix integral and make computations tractable. And then I will show the matrix model of the theory that we are concerned. And it's complicated, but we can see it part by part. The red part is the four-dimensional super Yamir's on half space, and the black part are the 3D gate node, and the green part are the 3D hypermultiplets. And we will study holography, so we can do the large N limit in the sense in which the eigenvalues can be replaced by some continuous eigenvalue density given by this rho. And this becomes, and this turns the problem into a 2D electrostatic description. So by 2D, I mean we have two coordinates Z and X, where Z numbers the gate node from 1 to L, and which is uniformized from 0 to 1. And we also have the eigenvalues, which is X. So this is a two-dimensional problem. And in the interior of the strip, we have the normal Laplacian equation with the source given by the D5 branes, the hypermultiplets. And on the boundary, there are two situations. If there is no 4D node, it's a normal delineate boundary condition. And if we have some 4D node, where we have the singular integral differential equation. So the second term is a normal, like the side point equation for super Yamir's, whose solution is the famous Wegener semicircle. And the first term encodes the bulk to boundary coupling, which makes the equation hard to solve. And the solution can be read off by the poles. So this integral have two poles. One is at x equals to y, and which cancels the contribution of the first term. And there is a second pole at infinity, which cancels the contribution of the second term. And in the end, the solution is written in terms of the generalized Lambert function, which is the root of some transcendental function, transcendental equation. And the first term is a sourceless solution, and the second term encodes the D5 brane sources. So this is quite technical, but actually there is a very simple way to read of the solution. So remember that all the information about the supergravity is encoded in the H1 and H2, the two harmonic functions. And the side point distribution is directly encoded by it. So the value rho is proportional to H1, and the eigenvalue is proportional to H2, and the gauge node is proportional to the harmonic dual of H2. So this is quite simple. The duration is based on Wilson loops, which will be explained shortly after. Okay, now we have the solution, and we will study observables. The simplest observable is free energy. On the gravity side, it can be computed by the area of extremal surface or something else. And on the field theory side, we can just evaluate the partition function using the side point. And for example, this is the defect energy for D3, D5 system, and where the D is roughly speaking the number of D5 branes, or a function of D5 branes, which of course match the gravity computation. And the second observable, which is more interesting, is Wilson loops. On the gravity side, there can be multiple Wilson loops. It can be in the fundamental representation given by a single F1 strings. And it can be also be antisymmetric K representation, which we can use some probe D5 pi brane. And there can be K F1 strings attached between the D5 pi branes and the D3 branes. In the field theory, it's given by the sum of the largest K eigenvalues. And in the continuous limit, of course, it just becomes an integral over the side point distribution. And one can also apply S-duality to the Wilson loops and to obtain the vertex loops. I will show the example of the Wilson loops in these three NS5 BCFT, which is very long, but it's agree with the supergravity computation, where they again numbers the gate node and K is the representation. And about the duration of the side point from supergravity, because the Wilson loops is the integration of the side point distribution. One can simply take the derivative of the Wilson loops. In that case, we can recover the side point distribution. So from supergravity, we compute the Wilson loops and take derivatives. We directly recover the side point distribution in the field theory. And in the end, as I showed before, the result is very simple and elegant. And at this stage, one can ask a question. In the holographic dual of BCFT, one may wonder which part of the full bulk solution is associated with the defect degrees of freedom, and which part is associated with the ambient degrees of freedom. This can partially be answered with the Wilson loops. So look at this left plot, where the colorful lines are the Wilson loop embeddings given by some D5 pi branes, the probe D5 branes. And the blue lines is some probe D3 branes, which can be think of as some four-dimensional observables. And then let's move to the right-hand side, the plot on the right-hand side. This part only supports the 3D Wilson loops, while this part only supports the 4D observables. So roughly speaking, one can think of the left side associated with the defect degree of freedom, and one can think of the right-hand side associated with the ambient degrees of freedom. There is also an intermediate side which supports both degrees of freedom, and the interpretation is less clear on this side. Then in the end, we will talk about one-point functions. It's also a simple observable that one can think of, but because it also has some independent interest from other communities, such as integrability communities or bootstrap communities. So this is the independent story. This is the simplest long vanishing correlation function in BCFTs that one can ask. Although the form is fixed by symmetry, but the coefficient AO contains dynamic information about the theory. And actually, a lot of computations has been done in D3 D5 defects, but they will focus on the quench limit, where the brane is given by the defect is engineered by a single D5 branes. But in our case, because we studied the holographic limit, the D5 brane is fully backcorrect, as like the question I asked before. So yeah, we have a lot of D5 branes, and this is not studied by people before. But the set point distribution has been derived with our method. And the operator is also the most simplest 1/2 BPS chiral parameters, which is just made up from the 6 scalars in super-YAMLs. And the localization has also been worked out by people before on the hemisphere, and it's just some polynomial a to the jth power. In the end, we want to study planar defects, which is given by such conformal transformations compensated by the operator mixing. And in the end, the one-point function is studied with this closed form in the large N limit, where the rho is given by our result, and the fj is the polynomial which accounts for the operator mixing. And then I will quickly show some examples. So this is a D5 defects, which has been studied by people a lot, as I have said, and our result is the extension. But for the more complicated case, such as the D3 D5 NS5 interface or BCFTs, where the 3D degrees of freedom contains many different fields, this is not studied before, and we have the first result. And I will just quickly show a simple example for D3 D5 defects or D3 NS5 defects, which are S-dual to each other. You see, the result is the same if we change the NS5 branes and the D5 branes while also invert the gauge coupling. And this is the S-duality covariance. And we can also recover the probe brane defect, the probe brane result by taking the number of fibrins to be very small. Yeah, so I have finished my talk, and I will quickly summarize it. The double holography in string theory can be engineered by D3, D5, and NS5 BCFTs in super YAMLs. And this gives the first principle construction with precision dictionary, although it's technically challenging, but it's still open to study. And then on the BCFT side, using supersymmetric localization, we study the set point of the BCFTs, and we provide precision test of ADS BCFT. And using such set point, we study the theory of the observables and, for example, one-point functions with back-correcting defects, and it has manifest S-duality covariance. Okay, thank you, and welcome for questions.
Thank you, Dongming. So any questions for Dongming? We have plenty of time left, so this would be a good moment to ask any questions.
Can I ask just one?
Yes, please.
Sorry, I missed something early in the talk. In the gravity solutions themselves, is the dilaton controlled as you approach the vibrating sources, or does it diverge in the gravity solution? I mean, normally it should diverge as you approach an NS5 brane.
Yeah, I think it diverge. Yes, it diverge. But then near the fibrine source, the supergravity approximation just break down.
Okay. So then you treat it as some kind of string or something beyond gravity in that limit. I see.
And this can also be seen from the matrix models actually. So, for example, this solution has the exponential tail. So for the large eigenvalues, it has an exponential tail, and which means there is some eigenvalues which diverge, and that's exactly correspond to this behavior.
So it matches.
Yeah.
Good. Great. Thank you.
Thank you.
Any other questions for Dongming? Okay, if not, we can thank Dongming and I can kill the recording.